Okay, here we are in the lab again, and this is episode number 13 of Build Your Own Main Brain Microcontroller. And so one of the things we haven't covered yet is the buzzer. So main brain has a buzzer, and when you power it on, it runs through its initialization routine, and when that's done and it starts the main program, then it beeps or buzzes, however you want to say it. So it's very simple, but I just made a change to the design. So all previous versions just use port pin. The latest is RA1 port pin, port A1, to just bit bang a frequency out and make it buzz or beep. So I changed that, and I just switched a pin. I think it's pin 40. We'll look at it. We'll go over it on the actual schematic, but I just changed the pin so that the PWM can get routed to it. You can either bit bang it like it is previously, or you can run the PWM to it and make it, change sound. It's a buzzer, so it's made to operate at a fixed frequency. But you could make some little tunes and stuff or different tones using the PWM. Be a little easier. You can still bit bang it too, but the PWM makes it a little bit easier. And so I just added that feature. It's just it's just a little added feature that took me like 5 minutes to change the schematic. And so there'll be a new revision up on the website. So if you don't know, antimatter.me is the support website for main brain. So you can access all kinds of data, the source code, schematic, the Fusion 360 files, all that stuff. All right. So that's what we're going to focus on. It's a simple thing, but it's kind of a fun thing too at the same time. And it's a part of main brain, so we have to cover it. And hopefully it'll be interesting. Let's take a look at the buzzer circuit. And we're in main brain schematic here. We'll zoom in. Right here's the buzzer circuit. So as you can see, it's a fairly simple driver circuit. We have a signal, and the signal comes from, well, the signal on the older versions prior to this video came from RA1 right here, pin 38. And then as I was talking, I moved it, and I mentioned 40, and I did move it to 40 at first to try. But it's what happens is when you program the device and update the firmware with the PIC kit, it causes a lot of static, like sound through the buzzer while you're programming, and I just didn't like that. I mean, it just doesn't sound professional for that to happen. So I had to move it from 40, and I moved it over here to 82, which is RD5, and this is RPD5, which is a programmable pin, so I can route the PWM to RD5 if I wish in software. Otherwise, we just bit bang it on RD5 the same way we were bit banging it over here on RA1. You just have to change the port pin in the software. And so that's where the signal comes from. Comes from the port pin, goes through a 180 ohm current limiting resistor, and it goes into the base of U4. And this is the part number. It's an NPN, regular NPN transistor. And so it acts as a switch and just switches the buzzer on and off. And the buzzer has a coil inside, and so it needs a diode. And just like any relay or coil, you need a diode to block the discharge current. And so that's pretty much it. That's pretty much it. So now we can take a look at how it's implemented in the software. Okay, so everything for the buzzer is in main C program, the main source program. And so as we come down, we call system setup, all right? And so as we hit system setup, we come down here, and this is the buzzer control. This is the older version, uses RA1. You take that out. We change it to, we have to make port D5 output, regardless of whether we use the bit bang method or the PWM. It has to be configured as an output. And then this sets the PPS feature. This sets RD5 to connect it to PWM. Now the PWM is in this microcontroller falls under the output compare module. All right, that's why it's called OC1. So we're using OC1 to be a PWM. So the OC1, the output compare module, can be configured as a free running or a triggered PWM. All right. And so we use timer 4, and that is set up right here. This OCA clock bit in the config register, set that to 1 for timer 4. If you set it to 0, it's going to be timer 2. And we use timer 2 for the backlight PWM. So we have to switch it to timer 4 so they don't interfere. So we turn on the timer. Timer is configured in the timer C program. And that's right here. So this is the initialization code for timer 4. And it has the interrupt priority and interrupt enable. It's set as a 32-bit, so it shares timer 4 and 5 become a 32-bit, and then we clear the flag there. All right, back to main. So then we turn on the timer. We set the source for the PWM, and for the X, let's see, we'll check that in this selects the X or the Y timer. So I'll show you what that means. We'll look at the data sheet. And so this is let's see, no, this selects which timer, whether it's 4 or 2. All right, and then this one selects X or Y. I'll show you in the data sheet. And so OCM, that sets the mode to be a PWM with no fault pin function. And so then we set the OC1 RS at 20,000. And OC1 RS is the secondary register value for to set the duty cycle. This isn't the actual number it uses. It uses OC1, I think it's S, but this latches it in, and then the next time a pulse, after the current pulse is finished, then this is latched in, and it sets the new period, the new duty cycle And that's the reason they do that is it's called like a double buffer way to do it, so that it doesn't like switch in the middle of a pulse and then create a skinny pulse or some glitch. So it's a glitch-free transition, I guess. And so I skipped over PR4 here. This is the period 4 register, for timer 4, the period register. So when you set this, it counts from 0 to this max. This sets the maximum count. So you can trim your frequency of your timer that way. All right. And so we set it almost maximum. And for most purposes, it's maximum. And then this sets the duty cycle. And so you can play with those numbers, and it will change the tone and the frequency and stuff like that. So, all right, so that's it for setting up the PWM or bit banging. You can do it either way still with this enabled, even with all this going, because the timer's going, but we haven't set the output compare module on yet. It just sits there and waits. So we come down here to the beep function, and that's where you can set how you want to do it. So this setup right now is for the PWM, and so right here we change, well, we set the prescaler to slow down. Actually, this shouldn't be 1 to 1. This should be 1 to 2 prescaler, because it's 0 is 1 to 1. 1 should be 1 to 2. All right. Then we set the period to a lower value here, because later on in the software, it may change timer 4, because you only use timer 4 to beep. So you can use timer 4 for other functions as long as it's not being used when you want to beep, right? So as long as you just jump back and forth between functions, you know, then you can use timer 4. And so so then we change this to make sure that it's set the way we want it for a beep. We make sure the timer's on again. We can, it's redundant. You can take that out from up above if you wanted. So then we just have a for loop used as a delay, and that is 10 million. All right, so it waits 10 million cycles, and then it turns the module off. I missed this here. This is where we turn the module on, then we have a big wait, and then we turn it off, and that's the beep. So while this is counting, it's beeping, right? It's sending a frequency to the buzzer. All right, so this is the old style. You can comment this. You can just not turn on the OC1 module, and you can just uncomment this, and then this is the delay for the old beep style. It has delay in there. Calls the delay function, delay 32, which is 32-bit delay function. And if we look at the delay right here, oh yeah, that's a long delay. This is a regular delay. Yeah, see, it uses T4. So a delay uses timer 4 as well as the buzzer. So you can't use a delay inside of this because you're using timer 4 to make the delay. So you can't use it with the PWM, right? You can't beep and use delay 32 function at the same time. So, but if you bit bang it, you can just do it like this here. Straighten that up a little bit. All right. So that is pretty much the functions to make it beep. And later, I'm going to add up in here, I'm going to pass it a value for maybe 2 values for the length you want to beep and maybe the frequency or something like that. All right. So, but that's pretty much it. And so let's look at some data sheets now. Okay, so here's the buzzer that I use. Magnetic buzzer transducer, it's called. Surface mount, low profile magnetic, means it has a coil inside, externally driven. So the rated voltage is typically 3.6 volts, all right? Operating voltage is 2.5 to 4.5. And current consumption is 100 milliamps. And so the rated frequency, this is the frequency that it likes the best. This is where it hits. This sound pressure, this level is measured at this frequency, all right? So 80 dB for the sound pressure level. Coil resistance about 15 ohms, blah, blah, blah. It's fairly small. That's about it. You got to be careful when you solder it on. If you get the flux inside of it, it'll stop it from buzzing, or it'll change the pitch of the buzz. So you got to be careful. It's probably the most critical part on the whole board as far as soldering, because it's a little tricky with that. But if you do get flux inside, you can flush it with alcohol, and it'll help. I flush with alcohol while it's buzzing, and the vibration like cleans out the flux and stuff. I've had that happen before. All right, so there's the mechanical drawing. Not much to it. Here's the example, and that's exactly what I have, except I used a different transistor, but it's pretty much equivalent. So this is the full circuit right here. This, it says 0 to 2.5 volts. I'm running about 3.3 into it. That doesn't seem to hurt it. I haven't really measured through this. I don't know what's actually hitting here. I'll have to measure it sometime. But anyway, that's our buzzer. Okay, so here's the data sheet for the microcontroller. This is chapter 18, the output compare module. So this is basically the block diagram. So as you can tell, we have a clock coming in. We have timer X and timer Y that you can select to bring it in, and then timer X, timer Y, roll over where it sets. And so then we have, see, the OC1RS and the OC1R. All right, so when you load RS, it gets transferred to here at the next pulse, right? So you don't do it in the middle of the pulse. And then it just compares the timer to this register, and then it sends an output. And you can trigger the ADC with it. You can use an output pin, which is basically what we're doing. And then there's an input. You can turn it on or off and control it with an external pin. And so here's our XY thing, right? So this is that OCA clock register. And so if it's a 0, then it selects timer 2. And if it's a 1, it selects timer 4, right, for OC1. So these are kind of set, right? You can't really change that. You can only change this 2. So you can use timer 2 or timer 4. And then the other one is selecting the X or the Y. So if you select the X, you get this choice here. And if you select Y, you get this choice here, right? So then, let's see, that's going to be, if we go to the control register, right here, we come down. So this is the OCX, meaning 1 through 8, and we're using 1. OC1 control register. So this turns it on and off here. This tells it to almost every module, or I think every module, can be set to stop in idle mode or continue. So for power savings, right? That's going to be a whole different chapter video on its own as power saving mode. And so you can do a 32-bit compare mode. We're using 16. That's just default. All the default is always zeros mostly. And so this is fault. If you want to have a fault status pin, you can do that, right? But so it either it stays zero if there's no fault, all right? And if you don't select the fault function, it's always going to be no fault. And so timer select. This is your X and your Y, right? So from the chart, then you can select your X and the Y's, which would be, if you have the other one 0 for timer 2, then timer X would be timer 2 and timer Y would be timer 3. All right, you have to look at the chart. It takes a minute to get the hang of it, what they're saying. And then this is the mode of the output compare module. So you got PWM mode with a fault pin enabled, and PWM mode with the fault pin disabled, which is the mode that we're using right now. So that's 6. So you can do these functions too with the output compare module. All right, and we'll probably talk about this more later in the output compare mode, other than the PWM, but I use the PWM a lot. All right, and that's it. That's it. So it had a couple notes here. This bit is only used when OCM2 is 111. So when that's PWM mode fault pin enabled, then if it's a 1, this one, it's always red as 0, right? Oh, I mean, it is red in all other modes, red 0 in all other modes. Sorry. All right. And then 2, that says refer to that table right here. And that's timer X, timer Y selection. All right, we went over that. Okay, so that's pretty much it for the output compare module. It's pretty simple to get a PWM to come out of it and switch it and stuff like that. So that's pretty much everything about it. So let's try to change the tone of the buzzer a little bit. Okay, so that's pretty much the buzzer and how we make a sound, make a beep. And so let's take and let's manipulate the duty cycle and maybe the frequency a little bit and change the tone. See if I can get the tone recorded on with the microphone. See if that works. It's kind of loud, so it probably should work okay. And so, yeah, let's manipulate that and maybe play a little tune. I'll see what I can come up with real fast. So this is the waveform of a normal beep of when mainbrain boots up, like we've seen in the code that we were looking at. So the way that code is configured, this is the waveform, and this is the sound that it makes. And so now let's go to the code, make a change, send it, update mainbrain, and see what kind of sound we get out of it. Here's our source code, and I brought this OC1RS variable down from the system setup. I brought it down into the beep function because if you set it in the system, it can change, then another program or function can change it, and then it wouldn't be set up for your beep. So I moved it down here so we guarantee that it's our desired setting when we call the beep function. All right, and then all the settings are in one area too, because you can change 3 things. You can change the period register of timer 4, you can change the OC1RS value, and you can change this uh, for loop for the length of the actual sound, the beep, all right? So there's three things you can change. So, well, actually four, because you can change the prescaler of the timer as well, right? So we have this set for a divide by 2 prescaler. And so the period register, the way it works is the timer always starts at 0. When you turn it on, it starts at 0. It starts counting upward. And when it hits this period register, then it overflows, and it can throw an interrupt if you set it, configure it to do that, right? But it overflows when it hits this setting in the period register, all right? That sets the frequency of our PWM. So the 2.7 kilohertz of the frequency of the beep is determined by this value right here, all right? And so this OC1RS register, this value sets the duty cycle, all right? So the way it works is the timer turns on, starts counting. The PWM pulse goes high. When the counter, timer 4, hits this variable, this number, this value, the PWM waveform goes low. And it stays low until the timer overflows. It goes high and starts all over again. And that's how you generate your PWM. So if you look at this hexadecimal number here, I just picked this arbitrarily and fine-tuned it a little bit with the scope. So this is actually, turns out to be 45,056. Whoops. All right. That's what this actually is. All right. So if you divide 45,056 by 2, that's 22,528. So that gives us a perfect 50% duty cycle. All right. And we will send that to main brain. And as you can see, that didn't change a whole lot, but it trimmed up our duty cycle to make 50%. So now let's change the duty cycle to where it's not high for very long. So a low duty cycle, because the duty cycle in the PWM is determined by how long it stays high. All right. So if it stays high 10% of the time, it's 10% duty cycle. All right. So let's change that to like 10% and see what it does. So if we want a 10% duty cycle, then we want this value right here to be 10% of this. So if we divide this by 10 and put it in there, we should have a 10% duty cycle. All right, so 45,056 divided by 10, well, that's a no-brainer. So it's 4,505.6, so we can't do the 0.6 and this variable, so what was it? Oh yeah, 4,505. You could say 6. It's not going to make that much difference. All right. Now if we send it to main brain, and you see that the tone hasn't changed, but the duty cycle changed by a factor of 10, right? So we're at a 10% duty cycle, right? So that's because the sound, the tone is based on frequency, right? So we didn't change the frequency, so we didn't change the tone, but we did gain power savings because the duty cycle, the time that it's on is reduced by a factor of 10, right? So that means we reduce our power usage by a factor of 10 for the buzzer, right? So the power usage of the buzzer was reduced by a factor of 10. So that could be an important aspect. So we just showed that changing the duty cycle doesn't change the tone of the buzzer, of the sound. So let's go back to our code, and we'll change the frequency and keep the duty cycle 10%, and we'll reduce the frequency and see what kind of sound we get from it. Okay, so now let's vary the frequency over time. So this is a fairly long beep. So let's take and run this into a for loop. Oops, not, oh. And whoop, less than, let's see, how's that going to work? That's going to be beep, and then it's going to switch. So let's go 10. And let's go, let's see what we get here. All right. All right. And then we'll put that inside here, like that. And so once it's in here, once it's done with that, then we will change the prescaler to divide differently and see what that does. Let's see. So if we go 7, because that's the maximum, and then we can just do I right here. Okay, we'll go A here, and actually we got to start at 1. And so then every time we come through here and we do it, we increase the value. All right, and 7 times, I think we can only go 6. All right, so the idea is it goes changes 6 times. So it beeps 6 times, but every time it beeps, then it divides the clock frequency by 2. And we'll see what that does. So you see that the tone of the buzzer did change as we divided the frequency to slower. I can't get it on the scope because it's like starts out high frequency and then it changes too many divisions for the scope to like show it all in one. But here is a graphic representation of it right here, and you see it's not linear, and it's probably because it's a buzzer and not a speaker. But we're divided by 2, but anyway, that's how you can use the PWM to control a buzzer or other things. But that's how we control the buzzer and make the sound and the length and the duty cycle, so you can use less power. And so there's a few things that you can do, and there's a few things, with it. it seems like it's such a small thing, just a buzzer, but there's engineering in it, and there's code writing and some stuff, math and things to think about. So that's the buzzer, and so that's it for this video, and I will see you in the next one.